Hello, welcome back to Chemistry Online. So, we last left off talking about electrochemical cells. Specifically, we talked about a voltaic cell, and in this lesson we are going to finish talking about voltaic cells and learn also about an electrolytic cell. That will be the last type of cell that we talk about, and so let's get to it. Okay, so here is our voltaic cell, and I call it a voltaic cell because there is a voltmeter on it, and voltaic cells are essentially batteries. So you can read the electricity, the power coming off of the cell by how many volts it is giving off. There is another type of electrochemical cell, and we will be learning about that in the second half of the video. The key difference, though, between the voltaic cell and the other cell that we'll learn about, it's called an electrolytic cell, is that voltaic cells give you power. You can read the voltage coming off of it, whereas an electrolytic cell, you have to put in the power to make the cell function. So, the last thing I wanted to talk about for our voltaic cell while we are here, though, is the voltage. So you can see that there's 1.10 volts coming off of this cell. That's the power that we're getting from it. And interestingly, it's actually the addition of the reduction potential here of 0.76 and this potential of 0.34. If you add them together, you will get 1.10 volts. So you should be able to have an idea of essentially how powerful your battery is based on these reduction potentials. And if you're wondering where we get them from, there's a table, and I believe these were figured out experimentally. They're all based off of hydrogen being 0. So this is just like a starting point. They said, okay, hydrogen is like the middle guy. We're gonna say that that's 0, and everything that goes up from there is positive, and everything that goes down from there is going to be negative. Now this table is called reduction half reaction. It's the standard reduction potential. So it's all based on the ability of the element to be reduced. So the more positive it is, that means the more easily it is reduced, the better it is at being reduced. Which makes sense because fluorine is a nonmetal, and as we said before, if we go back to our reference tables, here fluorine loves being reduced. It's at the very top of the reduction list for our table J activity series. And if you look at lithium, lithium loves being oxidized, and on this table, lithium is all the way at the bottom. It is the most negative number for reduction. It does not want to be reduced. It doesn't want to gain electrons. It wants to be oxidized. So, how does this work? Well, if we look at our diagram here, copper, as we said, has this positive 0.34 reduction potential. And if we go to the table, we will see that copper is right, where are you, copper? Copper is right here, and that is its reduction potential of 0.34. In the diagram, we oxidized zinc. So if I find zinc on this table, here's zinc, and zinc's reduction potential is negative 0.76. Again, it doesn't want to be reduced, and we didn't reduce it, we oxidized it. So we flipped this reduction half reaction to make it an oxidation half reaction, because if you look at it here, zinc is losing 2 electrons and becoming a positive ion. And because we flipped it to be an oxidation half reaction, we also flipped the sign of the reduction potential to be positive 0.76. Because these are all based on being reduction. So if you want to turn one of these guys who want to be oxidized into an oxidation half reaction, You flip the reaction and you flip the sign of the reduction potential. Then all you do is, you add these two together. So 0.76 and 0.34 added together gets you 1.10 volts. So you have an idea of how powerful your battery is. Of course, it's not going to be exactly what you expect it to be, but it should be close to it. Okay, so let's take a look at this cute little diagram I have. Here we have our red cat and our anox. Poor guys are stuck in their little electrode cells. And again, the ox is being oxidized, so electrons are going away from it over to the cat. And yeah. Okay, let's talk about electrolytic cells and electrolysis. So, as I said before, this is the second type of cell. All cells are called electrochemical cells. But then we have voltaic, which we just went over, and we have electrolytic. This is the other type of cell. And there are two really key differences between those two types of cells. The first key difference is that electrolytic cells are not spontaneous. They actually require electricity to run. So if you're going to make the cell, you're making it for a reason, to do something that is requiring electricity from you. So the things that people tend to use electrolytic cells for is electrolysis of a fused salt. So, you know, like this, at the start of the year, I reacted sodium. I'm sure you remember, especially my first period class when I blew up the beaker. So you can't get sodium that's that reactive with water naturally. There's no way. It would have already reacted with something. So the reason I was able to to attain that pure sodium was because somebody had gone in and done electrolysis and separated the sodium from whatever it was bonded to. Probably chlorine or fluorine or something like that. So that required a lot of electricity to do it, which is why it's expensive. The other thing that people put in electricity for and use electrolytic cells for is called electroplating. Those of you who like to look super nice, you know, and not spend too much money on jewelry, so like many of you might have silver-coated jewelry that aren't completely silver because pure silver is, you know, more expensive. So the way they were able to plate the outside of your ring or your necklace or whatever with silver is from electroplating, which requires electricity to bring that metal over to the electrode that has your earring or whatever on it, and then plates it with that metal. The last thing is splitting of water requires electricity to do that as well. And then you could use, after you split water, the hydrogen and oxygen separately as a fuel. They are currently working on research for trying to make this a more feasible thing. The problem is the output, the amount of energy you get from using hydrogen and oxygen as a fuel source, worth the amount of energy you have to put in to split the water. Unless they are able to split the water really efficiently, it's kind of hard to say that it's worth it. The other thing is, you know, hydrogen is super flammable and so is oxygen, so you gotta be careful once you do split it that you don't explode whatever you put it in. Okay, so there are actually cars that run on splitting water, the hydrogen or oxygen that comes off of it, but I'd be a little scared to be in those cars personally. Okay. Unlike a voltaic cell, an electrolytic cell is not spontaneous, as I said, and it uses electricity, so that was the first key difference. The other key difference between this type of cell and the voltaic cell is that the charges of the electrodes are switched. Previously, we saw that the anode was negative because that's where electrons were originally coming from and they were going over to the positive cathode. However, in our electrolytic cell, the anode is actually positive and the cathode is negative. The charges have switched. Now, the anode is still where oxidation is occurring. Anox still holds true, and red cat still holds true. The reason why the charges are switched is because now you are forcing electrons to go away from the metal that wants the electrons. So you are like, it's kind of weird to visualize, but they don't, normally electrons want to go towards the positive thing because electrons are negative. But here, this side is the side that wants electrons, but you're forcing the electrons to go to the negative side. So the anode is positive for electrolytic cells and the cathode is negative for electrolytic cells. These are the only two things that are the key differences between voltaic and electrolytic cells. So this is a diagram of the first bullet point I have, electrolysis of a fused salt. And you can see here we have a battery in the picture instead of the voltmeter supplying energy, and you have the two electrodes same as before. And now your electrodes are charged and they're going to attract the ions that are in the solution. So because your cathode is now negative, it's going to attract the positive sodium, molten sodium, and your anode, which is positive, is going to attract the negative chlorine from your molten sodium chloride. So that will effectively separate, so you'll have sodium buildup over here and you'll have chlorine buildup over here, and then boom, you can take your sodium and have some fun demonstrations with it. The other, and here, yep, your electron still is going from the anode, it's being oxidized, going to the cathode. Anox, red cat, still holds true. Oops. Okay. So the half reaction for, on this side, here your sodium is being reduced, it's gaining electrons at the cathode and becoming pure sodium. And then at the anode, you have the chlorine that is being oxidized. Again, the boxes mean the arrows. All of my arrows turned into boxes. I'm so upset. Here you have the oxidation half reaction because the chlorine, which was negative, has lost electrons, forming chlorine gas. And yes. Okay, this is the next bullet point of electrolysis from the previous page. Oops. Electroplating. So this is the second use of electrolytic cells, and electroplating is the process in which an electric current is used to deposit a layer of metals such as silver on the object to be plated. So in this case we have a metal spoon that we're trying to plate with silver, but you could imagine your jewelry or something also being here. And in this cell we have a battery being used because this is not going to just happen on its own. We have to force this to happen. And we have a silver bar as one of our electrodes, and the silver bar is losing electrons, so this is where oxidation is happening. So here we know our silver bar is the anode. Electrons are going up, and then here we have our cathode where electrons will be deposited. When the silver solid loses electrons, it forms silver ions, and then these silver ions, which are positive, migrate over to this spoon who has a now negative charge from the electrons being there. So it's attracted to the spoon